but thanks for inviting and thanks for the patience for the participants online. So I'm going to talk a little bit about joint communications and radar sensing, ISAC, integrated sensing and communications, which is the topic which we have been working more and more during the last couple of years. And then I will also talk about work on RIS, and of course they are interrelated. RIS is something we worked very extensively during the past five years or so in Ariadne project, for example, as was already mentioned by Markku, where he has been also an important contributor, and Angela and many others. Before going to that, a couple of very general slides. So I think all of us have seen this ITU, which was more or less agreed last summer and officially published in November on the different use cases of 6G. And there we have the good old broadband connectivity, URLC, and massive IoT, which were already in 5G, with slightly different names and evolutions, but they will be still there. But in addition, there will be this integrated sensing and communications, which is one reason why that field is now of broad interest. Then there will be integrated AI and communications, which I think, I'm not expert on that, but I think it means integration of on the service and application level, and also the use of AI in the radio level, which is something we worked on Ariadne in the RIS context, of course. And then there is this ubiquitous connectivity, which at least should hopefully mean connecting the unconnected. There are still billions of people with no internet connection, and hopefully that global issue will become resolved with this ubiquitous connectivity and 6G. And Markku mentioned the 6G flagship in Oulu. It started in 2018. It has sort of four main areas of research, focusing on wireless connectivity, devices, circuits enabling hardware technologies, also software technologies, mostly focusing on distributed intelligence and this distributed AI, which was part of the research agenda from the beginning. And then how to apply these in a sustainable way in different vertical applications. And there are many, of course, and we have identified 5, which we give currently special emphasis. It's big national program with hundreds of researchers in academia, and then quite a bit company involvement in different collaborative projects. So that's the, let's say, background where I'm coming from. Okay, let's now go showing some more highlights on the technical work which we have been carrying out. So before that, I will talk a little bit more about the ISAC motivation and use cases and what people anticipate currently in that front. Then I will say a few words about this dual functional radar communications, which is a special case of ISAC and the work we have been recently doing in that front. And then few, let's say, highlights from the RIS work, part of which done in Ariadne, some parts in some other initiatives. And in particular there, I'll talk about channel estimation and positioning, which are key ingredients which we need in ISAC and in this physical layer ISAC, where we do this dual functional radar communications. And then hybrid relay RIS, which is now somehow well known, but let's say maybe a little bit less studied in the beginning. Okay, first few words, generic words about use cases. So it seems to me that currently ISAC or joint communications and sensing, JCAS, they are considered as synonymous, although sometimes people make slight difference, so that ISAC is a wider concept and JCAS is a special case where you really do joint design and joint optimization. In any case, ISAC can apply techniques in the physical layer, application layer, network layer. It's quite wide term. And then when we as physical layer and RIS kind of people work on that, we usually mean dual functional radar communications or dual functional communications and positioning, so that we take the physical layer signals and use that to create a map of a radio environment, locate scatterers, locate objects, locate the active connected users, which we then call positioning. And the basic idea has been around for quite some time. There has been some works on, in particular, radar-centric view that you have radars, and then you'll see if you could use part of the resources to have some communications in the same bands in the cognitive radio manner or with index modulation, different things. But now our focus here is more on the communication-centric design. We come from the 5G background, legacy, and want to design 6G system, which is primarily communication system. But then if and when it makes sense, we use the services, infrastructure, hardware, and all that to do sensing tasks as well. 5G did some of that already for the positioning. Now 6G is expected to go beyond that. And where to use it, I'm not going too deeply into that, but 3GPP has already identified some 30 or so possible use cases. Some of them are, say, pretty broad, like surveillance. Some are pretty narrow, like some, let's say, quite particular weather monitoring use cases. I listed some examples here, trying to classify them a bit. But anyways, it's active field already in 3GPP. And as Markku mentioned, we have been, as an academic institution, more active in the pre-standardization bodies, like in these ETSI industry specification groups. And now there is a new one on focusing on ISAC, which had its kickoff in November. And the first plenary meeting was just, I think, last week. It was very recently. And it has currently 4 work items or areas of work, which are, as discussed, the definition of the ISAC use cases, deployment scenarios. Then there is a work item on channel modeling, measurements, evaluation methodology, system and radio access network architectures, security, privacy, trustworthiness, and sustainability, which is, of course, very important, because when you talk about sensing the environment, sensing the user's behavior, the privacy, security, all those concerns immediately are there. That work item didn't start yet. The other 3, the first 3 have already started. And this is somehow summarizing what the 3GPP and ETSI plan to do. So the idea is that now, before the actual kind of 6G standardization starts in 3GPP, obviously it's expected to start seriously next year. We have time for this pre-study, and well, then sometimes 26, 27, there could be the release 20, which might be considered as the first 6G standard. So now it's the time to do this pre-standardization and related research. And then going back to this terminology, and in HexaX, which is the European flagship project on 6G, we discussed in the early phases about how to categorize things, and I think the end result is quite nice. So we, and also I, tend to refer positioning as finding the location of a connected device, which is part of the network. That's kind of mobile positioning or mobile network assisted positioning. Of course, there are other global positioning satellite navigation systems which do the same, but that's a bit different. different world. Localization includes positioning, but also estimation of a position of a passive object. So in localization, the object is not necessarily connected to the network. Sensing includes positioning, but also, again, a little bit wider. So it's the functionality that you sense, observe the signals, and then perform inference to find locations of either connected or non-connected objects or shapes and such. And here as well, joint communications sensing is considered equivalent to ISAC, is the joint design, joint optimization, and reuse of the hardware and resources, and also frequencies for both communication and sensing services. The architecture work has already started. It's kind of initial, but there are, of course, in practice, you wish to connect the 6G and the terrestrial network, enabled sensing, localization, and all that to the satellite systems, and use both for the purpose whenever feasible, so that there is the satellite coverage available. Then we can use radar architectures. We can do monostatic, bistatic sensing, and so on. We can do radar-based multistatic sensing and so on. And as said, the security is important aspect. There is work on that, but let me emphasize that is very important consideration, because if there are security, privacy concerns, then this service will never fly. People don't want to use it and don't want to give the permissions to be sensed and assisted in assisting sensing and so on. Okay, then to this dual functional radar communications, what is the basic idea there? So a typical example which people have considered a lot is monostatic sensing, where we have a base station sending data, serving users in the downlink, and also simultaneously listening to the echoes of the radio signals like the radar does, so that we can locate some targets which are unconnected. And if there are resources like power, frequency resources, spatial resources available beyond what the current communication service requires, we can use those resources also to add a dedicated sensing signal, and that's what we may do. So we have a precoder, we have data symbols by which we serve the users in the cell area, but then on top of that we transmit a dedicated sensing signal, kind of radar signal on the same frequency band. Now, of course, there are how to say, link budget problems there, because in radars to have a good performance, you usually need very high transmit power. As everyone who has worked on radars know, they use typically much wider band much larger power than the communication systems do. So doing large area coverage to sense really airplanes and such may not be actually the main use case. I think the airplane is there more to provoke the thought. More realistically, this is something which you do indoor and combine for surveillance of some room, for example, or locating some objects in an industrial environment, objects which are not actively connected. So the range is you can provide by the power levels of typical cell towers are not very large. Okay, but this is anyways optimization problem which we can deal with. We can have two metrics, one for comms, the other for radar and sensing. And there are different ways to formulate that, and we will highlight few examples soon. And we can think it as a familiar problem, kind of modified beamforming problem. So if we have very loose sensing constraint, or the other way to say it is that if the communication traffic is so high that it takes all the resources, then we really cannot do much on the sensing. On the other hand, we can use much of the power for sensing, and then the communication rate is low. And if we have communication-centric design, that could happen sometimes in the nighttime or otherwise low traffic periods, when you could maybe sense the environment, for example. And then you can balance these two, of course. That's the balanced scenario. And there are different ways to formulate it. Communication-centric design could be, for example, that you maximize the communication. Well, this could be either way, depends on the values you pick. But one way is that you try to maximize the communications rate. So you do some sort of rate maximization. You can think it as, in some sense, communication-centric. And then you have, of course, the usual constraints, like if you have a large array with hybrid digital analog beamforming architecture, you have the analog phase shift constraint, then you have the power constraint, and then you have some constraint for the sensing. And there are different ways to formulate that. One direct would be, of course, that you wish to maximize the probability of detection of target, or if you know that there is target somewhere, then you wish to minimize the estimation of the variance of the location of the targets. Different such metrics, which often are quite complicated to be integrated to this pre-coding problem. So one common way to solve this is that instead of the directly optimizing the actual sensing accuracy, we may just take a desired beamform or beam structure from radar literature and then try to match to that as well as we can, and then maximize the rate with this constraint. And that is handy in the sense that it becomes then we have a constraint on the transmit signal autocorrelation, which tells us at the end of the day the shape of the beam. And then we try to design the weights of the beamformers to match that. And then we can merge this with our pre-coding problem so that we can do some rate maximization, which is somehow familiar for us. And then we have a different metric for the radar waveform. And then we can solve this for the hybrid digital analog precoders, which is kind of difficult problem on its own right, but becomes even more complex in some sense with the sensing constraint added. And I don't have time to go all these details, but we can design somehow familiar optimization problems, which we know how to deal with. And then we can find solutions to them, for example, by manifold optimization and various schemes. And one of our recent works extends that to wideband regime, where we do the optimization not only the spatial domain, but also with multiple subcarriers, so that we can use some of the subcarriers both for sensing and communications, or just for communications or sensing. Of course, this is easily quite complex, almost integrated programming problem, but we were able to devise some, let's say, first manifold optimization techniques, and then later simplify that by so-called deep unfolding, where the idea is that we take the iterative optimization, map each iteration as a layer of a neural network, and then use learning tools to adjust the hyperparameters instead of the, let's say, structured optimization algorithms. And that gives, that does not improve typically the performance per se, but it has in many examples reduced the computational complexity quite significantly. And then in one of the recent works which will appear in the radar conference this spring, we went one step further where we modeled the okay, we assume that we know that there is a target and we want to estimate its position while serving these multiple users simultaneously. We found out the expression for the Kramer-Rao lower bound, and then you can make a direct trade-off between the rate and the Kramer-Rao lower bound, which gives the bound for the estimation accuracy of the transmission. Here we simplified the model to make it the analysis tractable. We have just the maximum ratio transmission, which is not necessarily the optimum transmission, but anyways, we were able to shed light to this analytical problem. And there is a direct trade-off between the communications sum rate and the sensing Kramer-Rao lower bound with different numbers of antennas and different power allocations. Okay, but let's go now to the topic of the workshop. So some highlights of our recent works on RIS. It was again interesting to listen to Matthias's presentation, which really models the RIS as you should. So our model for RIS is kind of simple. We assume that we have phase control, and then we try to optimize the system performance or the kind of beamforming type gains, which of course simplifies the practical challenges. So my view is different and in some sense, of course, quite much simplified. Okay, I think I can skip this slide. This workshop, you know what RIS is. So we worked quite a bit on RIS channel estimation, and there still are relevant problems in that field, in particular when it comes to use of RISs to support positioning and sensing, localization, all those things. And if you look, this is not our work, this is generic, nice view from a nice survey paper. So we can, as you know, use RISs in two different ways, and we have also compared these views a bit. Either RIS is as it was in the beginning, something that you can use to enhance the propagation, and then the rest remains as in the conventional communications. You have transmitter, you have receiver, you have channel in between, and RIS is part of the channel, and then the channel estimation is only from the transmitter to receiver. You don't try to estimate the composite channels. And then the other approach, which we have also explored, just to understand what it would imply, is that you want to estimate the channel from transmitter to RIS and then separately from RIS to receiver, where RIS becomes more like a network element, active or semi-active device. And for the network element approach, we have done some works with some geometric channel models. Then that approach is unavoidably finding the position, orientation of the mobile arrays and all that stuff. So we create a model like this. And okay, then there are different approaches in the literature how you can estimate such a channel. Okay, maybe I will now skip that discussion in the interest of time. There are possible approaches in the literature. And what we did was based on the assumption that the channel is sparse, so that we have only very few multipath components, and we can assume sparsity in this scattering. And we have large array, and then we can do multiple trials. So we try different phase shift values for the RIS, and also different phases in the transmitter. So it's kind of beam scanning with the predefined codebook. And when we do that and apply a appropriate super resolution algorithms, like in this work we applied atomic number minimization, we indeed can estimate the channel, but it's the composite channels, but it's actually quite complex. Another approach is that we really merge the positioning and the channel estimation, so that we assume that we can estimate the position of the user to some extent, and we have some uncertainty interval for the position that enhances the channel estimation performance significantly with this atomic norm approach. And that's, of course, well, logical, makes sense, it's good. And it really says that if we go towards that direction, it makes sense to think RIS as a kind of network element, virtual anchor, which we use then also to locate the users. And that's what we have done in recent work, which we have just submitted to EUCNC this year, so that if we have a probabilistic model for the position, which we can obtain, for example, by this atomic norm minimization-based channel estimation, then we can create a factor graph and use different readily available numerical Bayesian estimation frameworks to find out the position. So we have looked at it from both angles. If we know the position, how we can enhance the channel estimation that we did already several years ago. And then the other approach, which we now looked, is that if we can estimate the channel with one of these schemes, how well we can estimate the position, and indeed we can improve the position estimate by this approach quite nicely. So my current conclusion, but I'm eager to discuss, I hope we can have a good discussion on this, is that it's a little bit philosophical what we want to do, and also definitely a commercial and practical aspect. But I think that if you want really to estimate all the channels, you probably in practice need to make RIS somehow active, so that it has either receive chains, transmit chains, or both. Or then it's something very simple. You just try to find out the good phase shifts, and then everything else in the system designs remains the same. But I'm happy to take any criticism if I missed something in my conclusions. And I think that both views have their benefits, and I would expect that both views may be used in practice, actually. Then, motivated by this, if we make RIS somehow active, what if we make it a little bit like a relay, so that we have a large RIS with phase shift elements, and if some of them would have the capability to amplify the incoming signal, so it would become a amplify and forward type relay element. Not saying that it's the thing which is easiest to do, but talking to our RF guys and such, they say that, well, you can probably do it with some level of accuracy. So we analyzed that that a bit, because, and the one motivation on top of what I already said is that many of the early works on RIS show that if you want to have a proper link gain and proper ranges, you need quite large RISs. You need a lot of elements, and then the control becomes complicated. What if we add a few amplifiers, not for all elements, but for some? Can we get a good performance already with smaller RISs? So that was another kind of practical motivation, and that's why we analyzed then the performance of the hybrid relay reflecting intelligence surface. So the idea is that there are few, maybe 4 or something, that's typical value in our numerical examples, elements which have a reflect amplifier or some device like that. And then for those elements, in addition to the phase control, we have also the amplitude control possibility. So it becomes a real beamformer. Now we didn't consider channel estimation in this work. We assumed that we have had a way to estimate all the composite channels maybe there is in practice a receive chain as well as in the RIS, which helps, of course, the channel estimation significantly. And then we try to do rate maximization with an approach where we have this rank one or the not rank one, power one unity norm constraint only for some of the RIS elements, and for the rest we have the typical power constraint like in the relay design. And we can see quite nice spectral efficiency gains, and also making assumptions on the transmit power, the overall modeling the overall transmit power from the transmitter and from the amplifiers in the hybrid RIS. We can also get, in many cases, energy efficiency benefits. Of course, it depends on the assumptions and the overall available transmit power, link budget, channel models. Many things have an impact. And to get a more realistic handle on the latter, we then extended this work to analyze it in the cell-free network, where we have multiple access points with, here we assumed in practice infinite backhaul, so we didn't, or front haul, whatever, we didn't focus on that aspect, but we made a pretty realistic model of the propagation losses and all that, and analyzed the performance. Here we modeled also the channel training, like people do it in the cell-free literature. So the training overhead is there. So the impact of channel estimation is also modeled in the performance analysis. And again, we can get, first of all, quite nice analytical performance characterizations in the sense that it's accurate. And with certain use assumptions, you can show that there are system-level benefits for the throughput with this hybrid relay RIS, which I think is interesting as a concept. How complicated it is to implement, what it takes, whether it pays off with that, that's something which I don't have an answer yet. So my conclusions and take on that is that this concept is also quite promising, but further work is still needed. Okay, I think that I have like a few more minutes, so few conclusions. So mostly the sensing model was quite simple. So that is something in the ISAC front, which we are now working on to expand. So have a more direct connection to this with sensing metrics and the communication metrics, not just the waveform. Okay, we had this one early work on Kramer-Rao bound analysis, but we want to do more on that. The hardware models have been quite simple. And then the cell-free work, which we have done, we want to extend also to cover the ISAC. And I think that in the ISAC and the sensing context, the hybrid relay RIS becomes interesting because, as I mentioned, the link budget, the power level you need for sensing the passive targets, like you know from the radar literature, that's quite high. Then it's indeed interesting to see how much passive RIS, active RIS, all these features could benefit for ISAC. And for that, let me just mention that in Ariadne, we also did quite a bit work on with our ray tracing simulator to study that how much the RIS benefit actually the link budget in different geographical configurations, indoor and outdoor. And here is just one illustration of some of our last year's EUCAP paper, which shows that if you smartly place a RIS in the left figure, you don't have, in the right figure, in the lower right corner, you have a RIS. You can increase the non-line of sight area, receive power levels quite significantly. So this is no ISAC yet, it's just the communications power. So there is clearly potential in this. This is a real outdoor environment. This is simulated result, but we have earlier made measurements on that area. Those measurements were without RIS though. Okay, so I think that that concludes my presentation, but let me just mention that some of you are coming, but within a little bit more than a month, we have 60 symposium in Lapland, so I hope to see you there.